All right. And we are live. We will wait a few minutes until everyone is in. We see still people trickling in after the great event yesterday. And then we will get started. Welcome back, everyone, to the Womanium Global Quantum Computing and Entrepreneurship Program. And today we will again have both parts because we have Corbin back here from Maybell Quantum, very innovative startup in dilution refrigerators. And after that, we will have a great lecture about quantum annealing by D-Wave. But first of all, I hope you really enjoyed the career fair yesterday. You got inspiration, you got opportunities, and you will take it further. Now you were in touch with the companies directly. And if you're looking for a job, or if you want to be in touch for a job later or for an internship, get back to them right away. Send that email to email addresses they provided, get in touch on LinkedIn and other ways, and take it further, referring to the great conversation that you had with them yesterday. We will have a second career fair come up on August 26th at the end of the program with the two companies that you see here, Maybell Quantum and D-Wave, also with IBM, IonQ, Quantinuum, Strangeworks. So that will be the second really great career fair. We look forward to having you there, and also we look forward to your feedback in the meantime, so we can all make that career fair an even better version. Then, without further ado, I would like to go to you, Corbin. Most of the people here have already seen you in the first week. Corbin Tilleman-Dick, CEO and co-founder of Maybell Quantum in Colorado. Corbin, you were at the Boston Consulting Group first, and then you decided to start your own startup in the quantum field, Maybell Quantum. Happy to have you for a virtual lab tour, and feel free to tell more about you, the company, and especially the dilution refrigerators.
Okay, terrific. Thank you so much for having me again. I'm going to go ahead and share screen, and I'm going to share the whole screen because I'm going to hopefully go a little bit afield. So the way that I'm going to do this lab tour, guys, is we are a small early stage startup, right? There are 14-ish people here any given day. And we're growing quickly to the extent folks are interested and want to reach out for jobs, please be in touch. We'll be at the career fair, but you don't have to wait till then. We are interested in hiring folks today, right now. But what I want to do is do a recap of what Maybell is, why it matters. It's a reminder that for those of you who were at my first conversation with this group, it may be a little bit familiar. Then go into a little bit more detail on what a dilution refrigerator is, how it works, and how ours are different, and then spend the last little while doing a tour of our relatively small facility here. So that's the plan. Feel free to reach out with questions. I'm sure the team will make sure that I hear them as they come up. But a reminder to everyone that the path you're on today doesn't need to be the path you stay on. And a couple of years ago, I had a realization that this path I was on that was really exciting and I was happy about was not the path I wanted to stay on. I had grown up in Denver, love it here. It's a fantastic place to live. Went to the Air Force Academy to study mechanical engineering and then Johns Hopkins. Had wife, kid, mortgage, and had made partner at BCG after 10 years. And in those 10 years, I was leading what BCG considered our, cutting edge technology advantage practice, right? And as part of that, I got to lead a bunch of deep tech work and talking to folks who were at the heart of quantum. I came to the realization, and I think you guys heard me say this last time, that quantum is going to be more important to the next 60 years of technology than the internet, the integrated circuit, cellular technology, than all of those combined have been to the last 60, and that I didn't want to be on the outside looking in. But as somebody who didn't study physics, who wasn't an expert on qubits, there was a pause for me on how I could really contribute to this industry. I firmly believe that problems only solvable by quantum are going to be key to the survival of the species. There are ways to reduce our impact on the climate without quantum. There aren't ways to turn back the clock on climate change without quantum. There are ways to reduce human suffering from disease without quantum. There aren't really paths to true personalized medicine without quantum. And I wanted to be part of this. And so what I set about to do with Maybell is build the picks and shovels for the quantum gold rush, right? The things that the physicists building quantum computers need in order to thrive and succeed at driving the innovations that will define the future of this planet, right? And what I saw as I talked to folks throughout the industry is that billions of dollars are getting invested by companies like D-Wave and Google and IBM and Quantinuum and all these other companies into quantum processor development, and for good reason. The processor is the beating heart of the quantum computer, and it's where, candidly, the most money is going to be made, and where early differentiation can be captured and well-defined. And the first company to have a full-scale fault-tolerant quantum computer, if they are well ahead of their competitors, that is a multi-trillion-dollar company as that processor rolls out, right? So it makes sense that they're all excited about that and spending time on that. The IBMs, Googles, Microsofts, Amazons, Intels, these companies that can throw billions of dollars at the problem are excited about that. Maybell was never set up to compete with those guys. What it is, when you Google a picture of a quantum computer, you get this beautiful golden chandelier that I think you've probably become very familiar with over the last several weeks of this program, and some of you were familiar with before. But what the Googles and IBMs and Amazons and Microsofts are working on is this tiny square, this black square inside the blue circle at the bottom of the golden chandelier. That is your quantum processor. And just a reminder, in order for that processor to function, it needs to get close to what I like to call quantum silence, right? A stable, shielded environment, very close to absolute zero. And the rest of the golden chandelier is the hardware that creates that environment and allows you to communicate with your qubits. And today, over 90% of all of the investment into quantum has been into companies that depend on dilution refrigerators. Some of them depend on it for the whole life of the qubit. Most of them do. If you look at a Rigetti, a Google, an Amazon, a IBM, a D-Wave, all of those, their qubits live in DIL fridges. Others, Xanadu, they have room temperature qubits. I don't know if you've talked with them yet. I love their tech. I think Xanadu's tech is incredibly compelling. But Xanadu's qubits are at room temperature, but their photonic readout is happening sub-Kelvin inside a dilution refrigerator, right? So there are only a handful of players out there that aren't dependent on a DIL fridge. And so the question then becomes, what is a dilution refrigerator? How does it work? Why does it matter? So most dilution refrigerators today have two separate cooling cycles. And most of them are what are called a dry system. The schematic that I pulled this morning is a wet system, but we don't worry too much about anything above this 4 Kelvin level. So we're gonna put that to the side. You basically cool down to 4 Kelvin, so incredibly cold, unbelievably cold, using a type of Stirling engine that leverages helium as the working fluid in that Stirling engine. And that's what is called a pulse tube, or in systems that require ultra low vibration, like Marlow's system, or older systems, you use a helium bath to get you down to that 4 Kelvin temperature, right? Below 4 Kelvin is where you have what's called the dilution unit. Now, interestingly, almost all of the cooling power in the dilution unit, there's a cycle up top that's called a Joule-Thomson that gives you an initial cooling power, but almost all of the cooling power is happening down here at the very bottom of the fridge. Once you're down to about 870 millikelvin, helium 3 and helium-4 undergo a spontaneous phase separation. Just like water wants to be solid at 0 Celsius, helium-3 and helium-4 don't want to play together as a single mixture below 870 millikelvin. And what you end up with is 2 phases of helium, one of which we call the concentrated phase, that's almost pure helium-3, and the other is a dilute phase, and that's 93.4% helium-4, and the remainder is helium-3. And that ratio is something set by God and nature and defined by the laws of physics, and it really wants to stay at that ratio. So helium-3 is special. Helium-4 you put in party balloons. You have a party balloon full of helium-4, and it's going to cost you what? Maybe $1, $2. It's not that big of a deal. If you have that same party balloon full of helium-3, it's going to be like a $10,000 party balloon, right? You get helium-3 right now by dismantling nuclear warheads, and that's basically the only way you get it. You can distill it. It exists in tiny concentrations naturally that you can find in like natural gas and stuff like that. But mostly it's by dismantling nuclear warheads. And in the future, you know, if quantum does what we think it's going to do, or if fusion does what we think it could do, we're going to be like mining the moon for helium-3. Super rare on Earth, super important, and absolutely necessary to achieve these ultra low temperatures. Because when the phase separation takes place, if you pump on the dilute phase, you are going to disrupt that ratio. The helium-3 is going to evaporate preferentially to the helium-4. And the heat of mixing, when nature tries to correct that ratio, is how you remove entropy from a dilution refrigerator. Everything else in the fridge is just about recapturing the cooling power efficiently that is taking place from that kind of the natural phase dynamics of helium-3 and helium-4. And so when we talk about discrete heat exchangers and continuous heat exchangers and all of the other pieces of a dilution refrigerator, it's because you can get the helium cold relatively simply. You know, you need something that can get it down to 870 millikelvin, but then you just basically pump on it. And if you pump on it hard enough, it's going to get cold. But transferring energy from your sample to your helium is really hard. And then making sure that you don't waste the coldness of the helium as you run this cycle, as you're pumping on it really hard, is also really hard. And that's what the whole dilution refrigerator is about. Now, dill fridges as they existed before Maybell really haven't changed much since the 1980s. This is one of the first dill fridges ever built. It was used to win a Nobel Prize for proving that superfluid helium behaved the way that we thought it would behave, we being theoretical physicists, not me. And if you colorize this picture, it would be almost indistinguishable from these other, you know, nice looking white dudes in glasses staring at a golden chandelier, right? That golden chandelier that everyone likes to talk about though, and we talked about this a little last time, it sits inside this blue trash can looking thing. And everything else in this picture is the auxiliary equipment that you use to get that helium cold, right? You've got a bunch of pumps and compressors. You've got a water chiller for room temperature waste heat rejection. You've got a gas handling system and a computational unit that, you know, makes things work. You have these dewars that you have to go and pour liquid nitrogen in every couple of weeks to make sure that your helium stays clean, because even tiny bits of, you know, hydrogen is like the devil impurity that we deal with here, but other things, nitrogen, oxygen, they can cause problems too. But even tiny bits of impurity can become solid in the system and block impedances and make your fridge not work. You know, if you want a symptom of how unrefined these systems are, yes, you can look at the fact that to swap your sample, you usually have to take apart the whole system, which is a little bit crazy. But for me, it's really this coil of tube on the ground here, right? That coil of tubes is a helium buffer volume that up until Maybell, when you bought a dill fridge, they gave you 60 feet of these tubes and they said, you deal with it. And I'll pull up, lest anyone think that I found an intentionally ugly dill fridge for this picture. This is at the Lawrence Berkeley National Lab and you can see that same, coil of tube on the ground. You can see this system's open, so all of the radiation shields are kind of scattered around. And this is the best fridge on the market before Maybell launched. I mean, this is a super high-end fridge, but you can see they are just they're a bit of a mess, right? By the way, this is this advanced test bed lab tour is fascinating, and I highly recommend that anybody poke around there. So it doesn't matter which of our competitors you're using, that fridge basically looks the same, right? You've got a big trash can looking thing, you've got the coil of tubes on the ground, you've got a tangle of wires, and you have a kit that your team puts together. What Maybell has released, and what you'll see today, although not with all the skins on it, because we're building the fridge, not using it, so we have it taken apart so that we can do some experiments on it, is a solution that is a fundamental transformation. It is simple, scalable, powerful, designed for the future of the quantum industry, and designed to be the backbone of quantum data centers, right? Where we've taken more functionality than has historically existed in our competitors' systems, 4 times more qubit capacity, and put it into a 10th the space. Now, all of those components that needed to exist for competing systems, they still exist in this system. It's just we've found ways to miniaturize them, to make them more powerful, more effective, more user-friendly. And the changes we've made really go from the foundation under the fridge all the way to the sample volume and to how energy is captured from the mixing chamber. So, for competing systems, if you have a highly sensitive sample, in many instances, you'll literally dig a new foundation for the system. You have to put them on the ground floor, you jackhammer down, you dig out, 10, 15 feet, you put rubber buffers all around, you pour a giant concrete pad, and you put your system on top of that in order to isolate it from the vibration of the world, right? In our system, we said, well, we could do that, or we could use isolators from optical tables, which are actually more effective. We take everything, everything above 1.5 hertz, so HVAC, foot traffic, trucks driving by. Those get isolated out by our, air pistons in this version, though we're moving to a mechanical version because it's a little bit simpler for our customers. Then inside the system, we have vibration isolation that makes it so that even the noise of the pulse tube, which is on the order of like 7 nanometers of displacement, so it's not much in the way of displacement, but the noise of the pulse tube is isolated out by internal springs and isolators, right? We've made it so that you don't have to take apart the system when you want to access the sample volume, though if you do take apart the system, that's easy too. We have these built-in carts. We've got a door on the front of the system. But that door is actually a pretty big innovation, taking something that, again, traditionally is a couple days of work to get it apart. You warm it up, you take it apart, you do your sample swap, then you put everything back together. You need several people over several days to do it. And ours, in many instances, you're just opening the door and accessing your sample in minutes rather than days, right? We've pursued novel approaches to making the heat exchangers both more efficient and more compact, meaning we can use less helium-3, the super expensive helium that I was talking about earlier, while still getting the same base temperature and cooling power from the fridge. And we've done that in an innovation-centered way that I think startups are kind of uniquely positioned to do. So that's what we're building at Maybell. And I'm going to stand up now, kind of walk around the lab a little bit, introduce you to the team a tiny bit, though they're going to be pretty busy. And then we'll stop and answer questions as they come up. But you'll see it's not a big lab, it's not a big place. So let's see, I'm going to try turning this around. And this is the brains of the operation. Where the team is actually doing the work. And most of our team, this before, like we have a few physicists. Jenny's a hardcore physicist, and Kyle, wherever he went, is a hardcore physicist. But most of the team is engineers. designing and building the system, making it more customer centric, making it so that it is easier to use. We have a lot of chemistry that goes on. This room is all about chemistry, working on novel heat exchanger technology. These are, actually, I probably shouldn't show that. I'm bad about that. And then we have our shop, our lab, where we have quantum wiring that we are developing in-house. We have a whole bunch of prototyping equipment, big lathe, big mill, big 3D printer that we use for kind of rapid prototyping. And then that was the alpha system, which was, it did its job. It taught us what we needed to know from that one. And this is the beta system that is turned on and happy right now. And that, again, the entire, multi-room setup that we were looking at in the other lab is for us, these two racks, right? And today it's actually a little extra messy because we just put in a brand new pulse tube to see how that works. And so far we're pretty happy with it. If anybody from CRYOGENIC's on, we think they've done a very nice job on that. And then this is, so usually this rack here, which is what we call rack 2. It's where the pumps and the compressor and the gas handling system and all of that go. Usually that is inside that pretty box there, but for ease of access for us right now, that is what we've done. And that's it. That's the team. That's what we're doing. And we've been able to drive incredibly rapid innovation by being, small and focused on customer needs, and focused on really listening to our customers, understanding what they want from their systems, where their pain points are, and how we can address them. So I wanted to leave 15 minutes open at the end for questions. I figure it's not much of a tour if it's just a monologue. I don't know what the best way to handle those questions is, whether they're coming in on Discord or whatnot, but let me pause there and see what folks want to ask.
This was great to see, Corban. And it might have been a short letter, but this is actually the real thing that is happening there. This is this is a day at Maybell, and this is what it looks like. So it's amazing to see. It is amazing to see the diversity of the team with physicists, engineers, chemists, as you said. I hadn't realized that much, that you are innovating in heat exchangers and other parts so much that you need really this chemical knowledge.
Yeah, I mean, really, it's interesting because the secret sauce of a dill fridge is the heat exchanger, right? Getting the helium cold isn't that hard, right? I mean, I couldn't do it, but Kyle could do that in his sleep. But every time you communicate with a qubit, you have to send information to it, and information is energy. And so you heat up the qubits a little tiny bit to communicate with them. But if you're communicating with them a lot, that heat builds up and you have to get rid of it somehow. And so getting the energy that you send down to your qubit to initialize it, to read it, to do anything to it, getting that out of the qubit through the metal of the dill fridge and into the helium is really hard. And you're optimizing across a few things. And in the 80s, they made a change. They went from kind of a copper powder heat exchanger to a silver powder heat exchanger that they sintered. And nobody has done anything new since then. So literally,
can you
since
explain
the
those
80s,
a bit more? I am personally familiar with them, but what is a copper powder based
heat
exchanger?
So with the heat exchangers, you're trying to optimize a few things, right? So basically, helium, when it gets that cold, it flows almost like an oil, a viscous film, right? And so you need a way to have as much surface area as possible for that helium to interact with. But you also need as many connections between these items as possible, the things that the helium's interacting with. And then you need the transfer of energy from between the two materials to be as seamless as possible. That's something called Kapitsa resistance. And it's really counterintuitive. I still am, my mind is blown by this every time I think about it. But the way that energy transfers when you're that cold is only through sound waves, right? And so in order to get the sound waves to transfer from a metal, which is what your qubits are ultimately going to be attached to, into the helium, there's a lot of reflection and resistance to that transfer. And so you want a material that makes that transfer as easy as possible. And that's why silver has generally been used, right? So the silver nanospheres, you can think of it almost like sand that gets pressed together. And if you were to pour honey on that sand, it's not going to penetrate very well into it. And so one of the big things that Maybell's been doing in order to miniaturize our systems and make them more powerful while using less helium and making the system overall this much smaller is pursuing these novel heat exchangers that offer better Kapitsa resistance. So the resistance of energy from passing between the metal and the helium is lower, while also providing better pathways for the helium to flow into the material and better surface area. And that ultimately is a chemistry and materials problem. And so there's a lot of chemistry that goes on, and there's a lot of process refinement around that chemistry. Because if we have the best heat exchangers in the world, but they cost 20 times as much to make, it's going to be really hard for us to deploy them to our customers. So yeah, that's been a big focus of the team.
It's also great to see that almost rudimentary things like 3D printers are very essential in the design process.
Absolutely.
How did you go about the idea? Because it seems like you innovated almost every single component of a dilution refrigerator.
Yeah, so the idea really came about from talking to customers, right? I'm not a quantum physicist. I wasn't in this ecosystem except for as a consultant, but talking to the senior scientists at a bunch of the big quantum players, it was really interesting because all of them could look me in the eye and explain to me with passion and conviction why they had the best qubits, right? And if they were, doing superconducting qubits, they'd say, we have 70 years of experience building fabs. There's no path to scale in quantum that doesn't run through a fab. Anybody spending their time on anything else is crazy, right? And then you would talk to the neutral atom folks or the trapped ion folks, and they'd say, why are we spending energy building qubits? Nature's already given us perfect qubits. Every atom is inherently identical. The idea that we're building these is completely crazy. And I realized that I had no way of figuring out who was right and who was wrong, and that joining any qubit player for me was a little bit of a lottery ticket, right? Because I didn't bring anything special to the qubit design, to qubit builders. And so I was going to be, quantum ambassador of some sort, right? Something like that, which, would have been great. The companies doing the work are brilliant companies full of brilliant people. So would have been interesting, but it wasn't really what I wanted to do. But these same people who would tell me they have the best qubits, all of them would universally say that their supply chain was a total disaster, right? That the tools they need to build quantum computers are, designed by physicists for other physicists. There are things that, like, today, if you want to buy a certain type of thermometer, you call a super senior person at one of the big quantum players and they make it for you in their garage, right? And that's just the only way to get this thermometer, right? And it was pretty clear to me coming from this business background that that's not a design for a scaled industry. And so talking to folks about where the biggest pain points were, where the systems that caused the most heartache, the most downtime, the most frustration were, it really quickly became clear.
Corban is freezing for me, or I am freezing for you. Could someone say
that the cryogenic system will help?
There you are.
There we
Corban.
go.
We're good again?
Freezing. You were back.
Yeah, you're back.
Okay.
But great. And one of the important things that you're saying, you listen to what the field needs. And that resonates with what Alan Brody said on Saturday. Your pitch is not what you want to tell them, but what they want to hear.
Yeah.
Ask questions. What is needed? And that is where you need to jump in. Great. I will ask you more questions, and there are many questions, Corban. So we will go into the mode of many questions and short answers. One of the questions is, do dilution refrigerators and other control devices together cost more than the actual quantum device with the qubits?
Way more. So your fridge is going to cost way more than the qubits that you put inside it. But even more surprising than that, your wires are going to cost more than your fridge. And so, oh, did I lose you guys? No, there you are. So it's totally normal for us right now to sell a fridge for, $700,000, $800,000, and then to put $1 million or $2 million worth of wires in that fridge. And so one of those little, every golden chandelier that you look at has these little loops in it. Every little loop, every individual trace there will easily cost you $4,000 or $5,000. And so the fridge costs a ton, the wires cost an astonishing amount, but it's really the integrated system that you're building.
Yeah, this is what we're talking about. Siddharth from India asks about laser cooling. Laser cooling is a dense compactor. Why can't you use that?
So some technologies do use laser cooling, right? Anybody working on neutral atoms in general, they're going to use laser cooling. Some of the trapped ion folks will also use laser cooling. Laser cooling is excellent if you're trying to cool an individual thing. One of the complications with qubits, though, is they're pretty sensitive. And so if you have a signal at room temperature that's loud enough to be heard over the noise of the universe, call it a watt of energy that you're trying to make clear and differentiated from the noise of the universe. If you send that watt of energy to a qubit directly, you're going to blow the qubit up, right? And so along the dilution refrigerator, you see these multiple stages in the fridge. And at every step in the fridge, you're actually, well, not every step, but several steps in the fridge, you're attenuating that signal. And so you're making the noise of the universe more quiet, and you're making your signal more quiet. And you're also filtering for just the signal you want. And so by the time you're down at the qubit, you're only sending in microwatts of energy to the qubit, but those microwatts are clearly differentiated from the background noise behind them. In order to do that, you generally have to go down a kind of tree from 300 Kelvin to 50 Kelvin to 4 Kelvin, all the way down until you're at the mixing chamber. And to do that, a dilution refrigerator is by far the best technology. You can't do that with lasers very well.
Yes, for different purpose. Great. Then Nasser from Algeria asks, do you consider using quantum computing to solve the design problem of heat exchangers?
Yeah, absolutely. We've talked about that as a team before, and
wow.
Eventually there will be the ability to kind of goal seek with materials, right? So we want a material that has these characteristics, and quantum computers are clearly theoretically superior for designing those compared with classical computers. They aren't quite powerful enough yet to solve the problem, but I fully expect that there will be an iterative process as quantum computers become more powerful, that they will help make the systems that build those computers better also.
That's amazing. Then Key asks, in the fridge, especially in the millikelvin zone, there must be a distribution of temperatures. How can you determine or know the distribution? What technique can be used?
Yeah, it's a really good question, and it's harder than you'd think, because in order to measure, you have to put heat into the system. And so you're using a really specialized resistance bridge and a really specialized thermometer to make sure that understanding the temperature on the fridge doesn't actually degrade the performance of the fridge. Now, the good news is you don't have to depend only on thermometry. There are also things directly tied to the pressures and flow rates of various systems in the fridge that can give you information on the performance at the mixing chamber, the 10 millikelvin zone, for how the fridge is running. But what we do now, because we're getting all of the specific specifications on the fridge, is put multiple thermometers down there and recognize that we need to take point measurements over time. When the system is running, the 10 millikelvin temperature you hear is really kind of an average temperature for the plate, but you're right that there's absolutely a thermal gradient across the plate. It's a smart and nuanced question.
Yeah, and maybe interesting to know is also that the calibration of the temperature sensors at those temperatures is also a challenge or a thing by itself, right?
Yeah, and example, you end up needing these fixed point devices where, just like you've got the 870 millikelvin phase separation of helium, you have other things that at specific temperatures go through specific transitions. And so you can use those to have a physics-defined validation of a temperature, and then to calibrate other thermometers that are resistance-based or whatever.
Yeah, for example, using different superconductors with different transition temperatures, and then you see the transition every time that defines your perfect temperature. Now, Sarah says, thank you for the answer and the tour. There is a question by Kumar Pratik. What is the difference between the alpha and the beta system that you just showed during the lab tour? It seems both were the same.
Yeah, the alpha system was really for us to say, can we build this in this small box and make it perform, right? There are a lot of innovations that we kind of knew we wanted to do, but that we didn't do in the alpha system because that was designed to be as straightforward a system as possible within the design constraints, right? But there are also things that we just learned by building the alpha system where, the first door was too small. Actually, even the second door we've decided is too small. We're making a bigger door on the systems we're shipping out. The vibration isolation on the alpha system, we use the same copper braids that everyone else uses. And we looked at it running with the copper braids and without the copper braids, and we realized that they just weren't doing what we wanted them to do. And that's why we took a big step back and said, if we really care about vibration, how do we design a system that actually minimizes vibration? You're always going to learn in a startup by rapid iteration. And the purpose of the alpha system was to teach us what we were going to get wrong. And a lot of that was related to manufacturability more than the dilution unit itself. But Maybell is absolutely committed to ongoing iterative innovation. And so the system that we launched at March meeting is less good than the ones that we're shipping to customers. And the ones we're shipping to customers
only 4 or 5 months ago.
Yeah. And the ones we're shipping to customers are going to be better, every 6 months, every year, as we continue to listen to our customers, refine our processes, and respond to the things that they say. We love these 10 things you did, but this one piece of the fridge is still driving me crazy. I don't know what that piece is. If I knew what it was today, we would have fixed it. But I promise that once we have, a bunch of customers there in the fridge, they're going to let me know, and we'll continue to refine it.
Juliana from Italy asks, the idea of creating a 2-rack version for the diluter and the superconducting QPU is remarkable, but can you integrate your solution in an HPC room, or would the noise coming from other racks pollute the results of the computation? Would you need to have a separate room for the quantum servers?
No, it's a perfect question, and it's what we've designed the system to do. So we have designed it to run hot aisle, cold aisle in any room that has servers, right? So if you have a server closet, you can now put a dilution refrigerator in there that can run a quantum computer. And so it's central to how we've designed the system, and it's why we had to do things like most server rooms have air plenums under the floor, right? And those vibrate. They vibrate a fair amount. And it would be a disaster if we designed a system that just looked like it could work in a server room, but actually still required all of the specialized infrastructure build out that competing systems do, right? And so what we did is we said, no, what would it actually take to run a quantum repeater node in a networking hub that is isolated for years at a time? And that's how we designed the system.
In the meantime, Lindsay, could you have a look if Alex and Sarah from D-Wave are already there? And if not, could you send them a message? And
these are great questions. I can keep going as long as we need to wait. Yeah. So these are terrific questions.
And I know our engaged participants can keep asking questions. Juliana, thanks you for the answer. Demi from Austin, USA, a business question. Who troubleshoots or repairs these fridges? I cannot imagine your local HVAC guy could help.
No, so for now it's the core team, right? And it's actually been a deliberate decision on our part to make sure that during these first couple years, the team designing the fridge also has to troubleshoot and repair it, because that way there isn't a degree of separation between the people feeling the pain and the people working on the next iteration of the design. We've made sure that this same team is involved in the assembly of the fridges so that they think really hard about, have they put a bolt somewhere that's going to make their life miserable when they're assembling it, right? And so we make sure that every member of the team is kind of cross-training across the business and sales side of things, across the physics side of things, but also across the assembly and design side of things. And by doing that, we hope to shorten the design cycles and make it, BCG had this approach that they called smart simplicity that was very much focused on kind of making folks eat their own dog food, right? That if they make something, they have to experience building it, they have to experience deploying it, they have to experience serving the customers. And we've tried to incorporate that into how we're running the organization, especially while we're small. It means that we're able to flex across roles more easily, but it also means that folks are feeling the pain if they put a bolt in a silly place.
And we also heard when you start a startup, the composition of the team is essential. Not only your technical ideas, but also the team. How did you go about forming your team?
It's really, so there are some people on the team, Kyle and Jenny, who are singular talents that there's just nobody else who knows the stuff they know. And you kind of have to scramble to convince them to join by doing whatever you can. There are others who it's more of a process. You look for applications, you see who fits, you do a lot of interviews, and you make some mistakes. And you'll never know what it's like to work with somebody until you're actually working with them, right? But I'm really proud of the team we've built here. I think that the team is brilliant, and I love being around them. And we're working together really quickly to build something that we're incredibly proud of.
Yeah, and what you point out about Kyle, he had a specific physics knowledge, and you brought in a very different background, which sounds like a great match. Lawrence also has a question about it. Lawrence from the Netherlands, how do your former BCG colleagues react on your recent accomplishments with Maybell?
They're pretty excited for me in general. Leaving BCG is always, I think anybody who leaves BCG, it feels like a heart-wrenching experience. BCG is a intense environment where you're on the road together 4 days a week, and you're often spending more time with BCG colleagues than with spouses, right? And so shifting away from that to a job where I'm usually, not always, startup is really demanding too, but usually I can be home for dinner with the kids. It's a pretty big transformation, but I think they're pretty happy for me and for what I'm doing.
I was muted. 2 more short questions. First, about that experience, Alex from Thailand, what are the most impactful and transferable skills and experiences from your previous journey at BCG to the quantum startup? We'd love to hear an example.
So for me, it was a lot of the human-centered design work that I led at BCG. So part of the tech practice that I led was focused on, rather than traditional development processes, what's called human-centered design, where you are prioritizing, observing customers, seeing how they're actually interacting with a system, not asking them what they want. There's that old quote attributed to Ford that if you'd ask people what they wanted, they would have said a faster carriage, right? And by watching customers, understanding how they're actually interacting with systems and designing for that, you get to better outcomes. That has been directly applicable to what we're doing at Maybell and has built a much better system than we would have without it.
That is great to hear. And the final question about Maybell's ambitions, Taha from Algeria. How small can such a refrigerator be with nowadays technologies? And can we hope someday this could be integrated with a laptop-sized system?
So not using a dilution unit, you won't integrate that with a laptop-sized system, but you also probably won't want to. In general, for the types of things that quantum is advantaged at, right now, I think with 5G, we're down to a 7 millisecond delay to hit the cloud. That 7 milliseconds isn't usually going to matter. And so your laptop will usually interact with quantum over the cloud. Now, there may be exceptions to that. You may want to have a small, ASIC style quantum chip in your car for real-time image processing, where those 7 milliseconds actually matter because it matters whether the thing crossing the road is a plastic bag or a rock, right? Maybe, and that day will come, and Maybell certainly is looking forward to those technologies that will enable that, to make sure that we remain at the heart of it. But I think that for quite a while, the primary mode of interaction with quantum systems will be over the cloud, and that is going to allow quantum to develop more quickly and to make transformations in our lives more quickly.
Thank you, Corbin. Very exciting to hear Maybell's story, to hear your story, and to have a sneak peek in the lab where everything is really happening. It was as if we could step in ourselves and get going with the heat exchangers and with the system, for which I know you also developed really nice software to control the dilution refrigerators. We will switch to the next program item soon. Alex has joined from D-Wave, Sara has joined from D-Wave, but first, Corbin, stay on for a minute. There is a very important question for you because there is some buzz on the Discord. And it has to do with the name of Maybell Quantum. Where is the name from?
So Maybell is the coldest town in Colorado. Tiny little town way up in the mountains. I used to camp there as a kid with my dad. And so part of it is just being named after that town, but it's also a nod to two things. The first is Bell Labs. We believe firmly that the next generation of industrial innovation is going to require a type of investment that candidly the IBMs and Bell Labs and folks like that used to make, and that had mostly disappeared for the last while, 40-ish years. We think that that's necessary, and so that's the Bell piece. And also Bell states in physics, and all of you guys, or many of you, will be familiar with those. So there's a lot of levels to the name, but it's a nod to Colorado, a nod to Bell Labs, and a nod to those who went before to define quantum physics more broadly.
Amazing. The reason I ask is that there has been this teaser on Discord. No bell, what rings? And suggestions were no bell, Maybell. Is Maybell developing a quantum computer in the dilution refrigerators that you make? And when?
No, we're not. We're really focused on the picks and shovels. So we're not building qubits ourselves, but we're trying to make sure that folks like D-Wave have the tools that they need to build the best possible system.
Okay, then the question back to all participants. This teaser is about the announcement for Friday's speaker, a unique speaker, a very big speaker. And it contains these elements. No bell. What could be the speaker? We talked a lot about cooling today, and the name was even dropped that we could go 2 orders of magnitude cooler than with a dilution refrigerator. It has to do with that. Keep guessing on Discord, and we might reveal something at the end of today's lecture. But first, we have D-Wave. Alex Koszegi, Sara, Ejtemaee, very welcome. Corbin, thank you very much again. It was great having you again, and we will see you again on August 26th.
Thanks so much for having me.
Welcome, Alex. Welcome, Sara. You are both from D-Wave. Alex is a technical sales engineer working now with organizations, seeing where quantum computing could make an advantage for them. But before that, you actually installed quantum processors yourself for customers, right? And Sara, lead experimental physicist working on the development of those quantum processors, not only quantum annealing, but also gate-based models. And very interesting, your background was not with superconducting qubits, but actually in trapped ion technology. So you are an expert in both. Alex, can you tell one more interesting or fun thing about Sara and the other way around before we start?
Oh, yes. Sara has probably the cutest dog that I have ever seen, and also the most well-behaved dog. It's very awesome.
Oh, wow. I hadn't expected that. Great. And Sarah, about Alex?
Well, Alex is very athletic, and I can never see myself catch up to her whenever we go and do something together.
Oh, you
Wow.
did so good last time we went rock climbing. Yeah, it's great.
You do that as colleagues as D-Wave, rock climbing. That is great.
Yeah.
In addition to that, we are very curious to hear about quantum annealing, an introduction to the process, see what D-Wave does. So we really look forward to your lecture.
Thanks, Marlu. Let me just share my screen here. Yeah, thank you so much for the opportunity to join you all. This looks like a very kind of intense and interesting program. And thanks to everyone too who's joining this talk today. I know it's probably long, so I do appreciate you sharing your time with us. I know we have an hour and a half, so there we go. I've kind of split this talk up into a couple different sessions. This first session deals with quantum annealing because that's what we do. So we'll talk about quantum annealing more broadly, and then kind of dive into how we at D-Wave have kind of implemented our qubits and then built out our processors. I'll show you a few videos of a lab tour so that you can see kind of, behind the scenes. And then we'll have a brief Q&A on this section of the talk. After that, though, I also wanted to introduce you to how we actually use our processors from an applications perspective. So we'll look at our cloud technology, talk about applications, see a bit of a demo there too. But first, we're going to start with the technology itself and with quantum annealing. So I wanted to start, I'm just going to move my controls out of the way. There we go. I want to start by answering the question of what is quantum annealing. And quantum annealing is an algorithm that uses quantum mechanical effects to find a ground state of a Hamiltonian. If you come from maybe a computer science or an optimization background, though, you might be more comfortable thinking about that as finding a global minimum of an objective function. But however you think about that, quantum annealing is really well suited naturally to solving optimization problems, because in industry, when we express an optimization problem, we're often looking for the lowest point on an energy landscape or the lowest point of an objective function, since that represents our optimal solution to our problem. So quantum annealing itself is kind of governed by this adiabatic theorem. And this theorem states that we start by putting a quantum system in the ground state of a Hamiltonian. And at D-Wave, we've chosen a simple Hamiltonian like what's pictured here on the left. Here we have one single global minima. And actually, to realize this state, we've put all of our qubits into superposition. So it's a very simple Hamiltonian that we begin with. And then if we slowly evolve this Hamiltonian with time into a more complex Hamiltonian, then the idea is that throughout this evolution, the quantum state or the processor will just stay in the lowest energy spot or configuration throughout. So then when we end up at the end of the anneal, we end up also in a classical state at this kind of global minima. And that's what we're able to read out. Oops. Here we go. So now we're going to look at this process in a little bit more detail. And the plots that I'm showing here, they're just a 2D representation of what we saw before. So here the black curves, those represent the energy landscape that we saw in the previous slide. This blue kind of dotted line here represents the wave function. So the wave function here indicates the probability at which our quantum system is in any particular state at a given time. So we can see that at the beginning of the anneal, there's just a single global minima. Our wave function is concentrated around this global minima. So there's a high probability that we're in this state of superposition, this ground state here. As we progress through the anneal, remember that our energy landscape is going to start to morph or transform. And with that, we get multiple shallow minima, like you can see here. And as this happens, our wave function is also going to broaden or delocalize across the minima. So now we have some probability that we could end up in any of these minima. This is where a lot of the kind of quantum dynamics or mechanics are occurring. So things like tunneling to kind of find or stay in the lowest energy state. As we continue, our energy landscape becomes more complex and more defined, and the wave function also starts to localize around the global minima again. At the end of the anneal, at this point, we're now in a classical spin state, and so we can read out the spins of our qubits, and that becomes the solution to our problem. We can also describe this process mathematically with the transverse field Ising Hamiltonian. So that's what I'm showing here. You'll notice that there are two terms that contribute to this Hamiltonian. The first term here is the transverse field Hamiltonian, and it's responsible for putting all of the qubits into superposition, which allows us to realize this initial, more simple kind of energy landscape. I don't think I mentioned it before, but it's also worth noting that when we look at these energy landscapes or think about them, we can also think about every point on them as being a possible solution, and then the optimal solution at the global minima. But, as we start to anneal, though, we start to kind of turn on this second term in the Hamiltonian. So that's the problem Hamiltonian. And at this point in the middle, we have this contribution from both terms in our Hamiltonian. Then as we continue to the anneal, to the end, at this point, we only have a contribution from the problem Hamiltonian, and this energy landscape is fully defined by the problem that we want to solve. So as a user, if you wanted to solve an optimization problem or maybe a quantum simulation problem, you would be characterizing these H and J values. So another way to think about this is that the H values are linear biases on the qubit or linear biases in your problem. And J values are quadratic biases on your qubits or in your problem. So they encode a relationship between qubits. We can also think about this process of annealing in terms of what we call the annealing schedule. So that's what I'm showing here. On this plot, the vertical axis is the energy. The horizontal axis, this S parameter, is what we call the normalized anneal parameter. When S is equal to 0, that indicates the beginning of the anneal. And when S is equal to 1, that's the end of the anneal. We use S because users can actually choose their annealing time. So for our latest Advantage system, users are able to choose anywhere from 0.5 microseconds for an anneal all the way up to 2000 microseconds. By default, though, it's set at 20 microseconds. So if you didn't want to tune that parameter, you don't need to. This blue curve here represents our initial Hamiltonian. We're going to call that A of S right now. And this green curve here represents our problem Hamiltonian or our final Hamiltonian, and it's represented by this B of S term. At the beginning of the anneal, we've already talked about this, but at this point, all of our qubits are in superposition, and we have an energy landscape that looks something like this. This makes sense because we see that our A of S curve is fully on, so it has a high energy at this point, whereas our B of S is set to 0, so it's completely turned off. Then we start to progress through the anneal, and we start to turn off A of S while we turn on B of S. And it's worth noting that there's a fixed relationship between A of S and B of S at any point in the anneal. Though the anneal schedule can be modified slightly, the one thing that can't be modified is this relationship between A of S and B of S. It's fixed. As we approach this kind of point where the curves meet or cross over, this is where a lot of the kind of interesting quantum mechanics happens that applies to the problem Hamiltonian, so a lot of tunneling. And then as we continue to progress beyond that point, our qubits start to freeze out or collapse into a classical state until we reach the end of the anneal at s equals 1, where all of our qubits are in a classical spin state, and we can read that out. Okay, so we've talked about quantum annealing at the global level. So now let's take a look at how quantum annealing impacts an individual qubit in terms of its energy landscape. What I'm showing here, this plot, is a representation of the energy landscape of a single qubit at the end of the anneal. So that's when the qubit is fully characterized by this second term in the Hamiltonian. What we're looking at here is what we call a double well potential. So this is showing us that a qubit can end up in one of two states. So one state is spin down, as indicated or represented by this potential on the left. And the second state is spin up. And that's shown or represented, I guess, in this well on the right here. We can map these spin states to binary states, and this tends to be a little easier when we're using the quantum processing unit for applications. So the spin down state can be mapped to 0, and the spin up state can be mapped to 1. So we can work in the binary space as well. Now, what we're looking at here, I did mention that this is the energy function for the end of the anneal. And so this is representing the qubit in a classical state. But we need a way to move the qubit from superposition into a classical state where it either ends up in a spin down or a spin up. And the way we do that is by using this transverse field Hamiltonian to tune or move this barrier from 0, so down here, when it's at 0, we're in superposition. And as we raise this barrier up, the tunneling between states starts to slow, the system dynamics start to slow, and then the qubit will collapse into one state or the other. Now, the other parameter that applies to a single qubit is this H parameter, or this linear bias. And the way that we physically implement that, or physically think about that in terms of an energy landscape, is by kind of tilting this double well potential so that we make one state more energetically favorable than the other. And in this case, we can see that the well that represents spin up is slightly lower than the well that represents spin down in terms of its potential energy. So that means that it's more energetically favorable for the processor to choose spin up for this qubit state by the end of the anneal. Now, the last parameter we have that impacts individual qubits is this J parameter, which encodes a relationship between them. So this J allows us to say, sorry, Marlu, I see that you unmuted. Did you have a question?
Great. Yeah, there was a brief question. What do you exactly mean by the end of the anneal? How does the anneal happen?
Ah, yeah. How does the anneal happen? So we're going to talk a little bit more about devices, but the anneal happens by kind of turning off, or by changing the contribution of each of these Hamiltonians throughout a period of time. And there are many ways on chip that we control this. So we'll talk about a couple of the devices that we use to implement a qubit and a coupler. But we have on-chip control circuitry that allows us to start with all the qubits in superposition here. And then over time, we start to kind of ramp down this Ising Hamiltonian while turning on the problem.
Wonderful there. Thank you for the clarification.
I hope that helps. Feel free to ask more questions, though, if I miss something. Yeah. Yeah, okay. So then the last, well, for the purpose of this talk, the last parameter that impacts a qubit is this coupling with another qubit. So this is how we encode relationships between qubits. So we can say that we want two qubits to agree or have the same states, they're both spin up or they're both spin down. Or we want qubits to disagree and one's in spin up, one's in spin down, or vice versa. So this is an example of a relationship that we can program, and it can coordinate, or impact how or where the qubits end up in terms of which well they end up in or which classical state they end up in at the end of the anneal. Just maybe pause for a moment in case another question pops up in the chat.
David from the US asks, during annealing, AS decreases while BS increases. Is this true?
Yes. Yep, exactly. Yeah. So at the beginning of the anneal, A of S, we can think about it as maybe the term that contributes to the quantum mechanics or the dynamics in the system. So we start with the system dynamics really high, and then we want to eventually arrive at a classical state that has a solution to our problem, right? So over time, we want to slowly kind of ramp down the system dynamics and allow the system to kind of stay settled in a low energy state that represents, or a low energy state of our final Hamiltonian. So we use this relationship between A of S and B of S over time to kind of control how we move from superposition to a classical solution for our problem.
Wonderful. Further questions we ask later.
Yeah.
There's also a raised hand, Alex.
Sorry?
Somebody has their hand raised. ANNEALING, I think.
Oh, yeah. Amirali, if you have important questions, we will see them on the Discord.
Okay.
Thank you, Alex. Please go ahead.
All right, thank you. Okay, so now let's talk about how we physically implement our qubits and our couplers. So we use superconducting flux qubits at D-Wave for our qubits on our processors. They are RF squids, so we can think about them in their most simplistic terms as being just a loop of wire that has current flowing through it. And if you remember from an electricity and magnetism course, if you have a loop of wire that has current flowing through it, you're going to get a magnetic flux through the center. So you'll either have a magnetic flux pointing up or pointing down through that loop, depending on the direction that the current is circulating in, and according to the right-hand rule. Now we use superconducting materials to fabricate our qubits. And the reason we do so is that superconductors have a few really interesting properties when they're cooled down to a temperature that's low enough. One is that they have no resistance. So current that's flowing through a loop can flow forever. There's no power dissipation. But the second property that's maybe a little more relevant to our discussion right now is that you actually get current flowing in both directions at the same time. And so that creates the state of magnetic flux pointing up and down through the qubit at the same time. The flux doesn't cancel each other out. And so it's the direction of flux through the qubit that we use to indicate the state of the qubit. So at the beginning of the anneal, when our qubits are in superposition, we have current flowing in both directions. And then as we kind of progress through the anneal, that's going to change so that current is only flowing in one direction and we get a flux only pointing up or down. And that's how we interpret our spin up and spin down states. Now, if we were to leave our qubit as just this loop of wire here that has current circulating in both directions, we would only ever be able to put it into the state of superposition. There's no way to kind of change that into a classical state as long as it's a single loop of wire like this. So the way we get around that is we kind of break the wire at a location and we insert an insulator in that break. This is called a Josephson junction. And there will be a current that flows through that junction, which is called the critical current. The critical current is what defines that barrier height that we were looking at before. So remember how we go from superposition and then we raise this barrier up to a point where the qubit kind of collapses into one state or the other. The maximum height of this barrier is determined by the critical current through this junction here. Now, if we leave our qubit as is here, now we have a fixed barrier height. So with this circuit that we're showing, we can't tune the barrier. We can't move it from 0 up to this fixed height. So the way we get around that is we replace that Josephson junction with a loop that has 2 junctions in it, like this. This is called a compound Josephson junction, and it enables us to raise or lower the barrier height. And we can do so by applying a flux to this loop. So when we apply a flux to this loop, it allows us to change the effective critical current through the junctions here. So by changing that effective critical current, we can change this barrier from 0 all the way up to some height here. The other parameter that we talked about that impacts a single qubit is the linear bias, so this H value here. And we physically implement that H value by applying a flux to the body of the qubit. So that flux can either kind of bias or set a preference for that qubit to be in one well or the other. Now, the last thing we talked about when we talked about annealing was that J parameter, so that interaction between qubits or that relationship between qubits. And the way we implement that is with another qubit-like device. So you'll notice it looks very similar to a qubit. It's just fabricated with different parameters. So it'll have a different IC, it has a different inductance in the loop, and a few other parameters as well that allow us to operate it as a monostable RF squid. By operating it in this way, it creates a tunable mutual inductance. So we can apply a flux to this loop or to the coupler here, and that'll create an inductance or mutual inductance between these 2 qubits that are connected on either end. So the relationship between the J value that as users we would define and this flux that goes through the loop is shown in this plot here. And so when the flux through the loop is smaller, we operate the coupler with a positive mutual inductance. And through this equation here on the right, the mutual inductance is related to the J through the persistent current, which is just the current that is circulating through the loop of, or the body, the main loop of the coupler. But the main point here with this equation is that M, or the mutual inductance, is directly related to J in this way. So when we have a positive mutual inductance, we also have a positive J. So what that means is that if we want to program an antiferromagnetic relationship between 2 qubits, we need to choose a positive J value. And we can see that that mathematically works out as well, because if we have an antiferromagnetic relationship, that means one qubit will be spin up and one will be spin down. Mathematically, we would represent that as a +1 and a -1. So if we multiply +1 and -1 together, we get a -1. And then if we multiply -1 by J, we're going to get a -J value. So a negative energy value indicates a lower energy value, which is going to make that configuration more energetically favorable from a mathematical perspective. So we can see that having a positive J value, it mathematically makes sense as well for encoding an antiferromagnetic relationship. Likewise, as we continue to increase the flux through the qubit, we move the mutual inductance into this kind of negative range here. And that's how we realize a ferromagnetic relationship. So from a programmer's perspective, a negative J value will give us this relationship where qubits want to be in the same state as each other. Okay. So now that we know a little bit more about qubits and couplers, let's take a look at how we would lay this out to build a processor. So we can take our qubits and kind of stretch out those loops into something that looks like this. And then we can kind of tile them out to create, here we would call this a unit cell of 8 qubits. So we have 4 horizontal qubits and 4 vertical qubits. Notice that this one qubit that's highlighted in orange, it overlaps with the 4 horizontal qubits. And on the ends, we can also see this little line here that's connecting it to the qubits on either end. So this is significant because it means that for a qubit that's in the middle of the fabric or middle of the processor, we can add a coupler at each of these junction points. So at the end of the qubit, where each of these qubits overlap, and then again at the end here. And that allows us to couple a single qubit to 6 other qubits. We can then take this kind of tile here and just tile it out to create a processor, connect a bunch of these tiles together, and we can get a processor of about 2,000 qubits. So this is how we built our older generation quantum computer that has the Chimera architecture, which is what we're showing here. Now, recently, actually about a year ago now, we released the Advantage processor, or Advantage quantum computer. And that has a processor that is much larger, both in terms of number of qubits and connectivity. So we're looking here on the right at the architecture. I know it looks much more complex because it is, but still at the base, we're using this kind of unit cell idea. We've just elongated our qubits and kind of shifted them. So if I look at this kind of dark blue set of 8 qubits, you know, it does look kind of similar. And if I look at just one of those horizontal qubits here, you'll see that this kind of elongated and shifted qubit allows us to overlap with many more vertical qubits. Again, we can also couple to the qubits on either end, and then there's an additional coupler. It might be hard to see, but there's a little line connecting these 2 horizontal qubits that are close together. So with this topology, a single qubit is able to be coupled with 15 other qubits. And this is really significant because when we build out a full processor, like I'm showing here, here we're just representing it a little differently, where dots are qubits and lines are couplers. But here we can see that the Advantage processor is much larger, so it has over 5,000 qubits. But the significance of having a higher degree of connectivity or more couplers means that we can solve more complex problems. And from an industry perspective, that's really crucial to adding value to our hardest business problems right now. Okay, maybe I'll pause here just to see if any questions popped up, because I want to jump into a lab tour next.
There are great questions, but we can also ask them at the end.
Okay, perfect.
I know you will show a lot more.
Yeah, that's true. Okay, sounds good. Okay, let me change what I am sharing. Okay, can you see my screen now that has YouTube on it?
Yes, and it's not in full screen mode. Yes, there you go.
Perfect. Okay.
Perfect, great.
Let me just figure out. I need to send the audio through. Okay. All right. So I have kind of 2.5 videos to show you. Yeah, just of a lab tour. So I'm gonna kick it off now without further ado.
I'm Jeremy Hilton. I'm the Vice President of Processor Development at D-Wave Systems. I'm responsible for the Processor Development Group, which involves the design, test, and development and release of the quantum processor that D-Wave makes, which is the underpinning of the quantum computers that we build. Each of these black systems is a quantum computer. Inside that system is a thumbnail-sized quantum processor. In order to operate and develop quantum processors, we require a fairly extreme operating environment, which includes ultra-low temperatures and an ultra-low magnetic environment. And to achieve those, we need a fairly large and sophisticated system. The main room behind us houses the quantum processor, and the data racks in the front hold the quantum server, where users can access and program the quantum processor. And the other data racks include the cooling system, which includes pumps and is responsible for the chirping sound you can hear in the background. Inside the room, before we get to the quantum processor, there are many layers of shielding which allow us to create the low noise magnetic environment the chip sits in. If you look inside the data racks, you'll see that they don't contain what you would normally expect. So here we have some scroll pumps, which are mechanical parts associated with pulling vacuum on the fridge inside the room behind. So this is obviously highly unusual for a data rack, but has been integrated so that it wouldn't look out of place in a data center. And in fact, the requirements for running the system are consistent with all the services that would be available in a data center, which would include chilled water and power predominantly. In this rack is the quantum server, which allows users from anywhere in the world to interact with the processor itself. This server is receiving information from users, converting that into the machine language of the processor, and sending that machine language into the room behind, where high-precision analog electronics will convert those signals into electrical pulses, which are sent through cables into the refrigerator and down through the cooling system to the ultra-low temperature of the processor. It executes its problem, and then data from the processor is returned to the server and returned to the user. And the system is very flexible, and that users can be programming in whatever language they're comfortable with, and interacting with it either with this system in their data center or even here in D-Wave's lab. The quantum bits in our processor store information in the form of little magnetic fields. The 0 and 1 correspond to a little magnetic spin. The controls over the qubits are all in the form of magnetic fields. So the quantum processor is very sensitive to magnetic noise and the magnetic environment that it sits in. In order to keep that magnetic environment really low, as well as support the ultra-low temperature that it's operating at, this system behind me has about 16 layers of shielding between where I'm standing and where the chip sits at the center. These black panels are really for aesthetic purposes, and they integrate these data racks with a shielded room, which is the first of those layers of shielding, and is filtering out RF signals. So if you were to stand inside the room and close the door, your cell phone would stop receiving a signal. The fridge itself has a combination of radiation shields as well as magnetic shields, which help support the ultra-low temperature operating environment and achieve the ultra-low magnetic field. Inside the room, we have to keep electromagnetic noise very low. So even things like power outlets aren't allowed, because power can be quite noisy without extensive filtering. So inside the room, we have the cooling system, and these are radiation shields. So this is the next layer of shielding inside the room. The chip itself, the quantum processor, is sitting at the bottom of this array of shields. And this is, again, the first of several more layers. Inside these shields is vacuum, which is the insulation of the cooling system. When we want to swap the processor or conduct maintenance on the fridge, we warm the system up, we remove these shields, and then the processor is accessible, as well as all of the internals of the refrigerator.
My name is Murray Tom. I'm the Director of Professional Services at D-Wave. I talk with our customers and partners about what quantum computers are, what kind of problems that they solve, and work with them to develop software that uses quantum computers. We're standing inside a quantum computer, and you may know that the quantum world is delicate. It's easily disturbed. So there are many layers of shielding in this system, which we've removed in order to look at the internals here. A traditional supercomputer may have many thousands of processors in it, but in this quantum computer, there's only one chip located right down here. When you send an instruction to the quantum computer, a delicate quantum calculation is taking place on that chip to produce your solutions. The system we're looking at here is an ultra-low temperature cryogenic fridge. Because it works at such low temperature, we use the Kelvin scale to measure how cold it's getting. In the Kelvin scale, a warm room is like 300 Kelvin, and 0 Kelvin is the lowest temperature that can be reached. Physicists refer to it as absolute zero. There's two levels of cooling in this system. The top one is a pulse tube refrigerator, which takes us from 300 Kelvin to 50 Kelvin, and then down to 3 Kelvin. This is roughly the temperature of interstellar space. And then a second refrigerator, a dilution refrigerator, takes us in this plate from 0.7 Kelvin, 0.1 Kelvin, and then down to 0.01 Kelvin. When the system is operating, this plate and everything mounted below it is 10,000ths of a degree above absolute zero, which is more than 100 times colder than interstellar space mounted here. And this whole system is designed to sustain those low temperatures in a continuous cycle. When you send an instruction to a quantum computer, the signals pass down these wires along the sides of the refrigerator. And at this point, there's a break in the wires where all the signals become superconducting. Superconductivity is this amazing effect where you can send electrical signals without any resistance whatsoever. So the electrons aren't even interacting with the atoms in the wires around them. That's great because it means that this portion of the system has no energy dissipation, it produces no heat. But it also means that we can't rely on the wires to cool the electrical signals and eliminate their noise. So we have a custom filter bank mounted here which cools those electrons. An important aspect of the superconductivity is that these signals and the quantum processor unit consume virtually no power, whereas the supporting systems around it consume about 15.5 kilowatts. And this remains the same regardless of which processors are installed at the bottom. If you were to take a fully populated server rack out of a traditional supercomputer, it might consume 10 times that much power. So for our first customer, Lockheed Martin, when they upgraded from their first chip to the D-Wave 2, they saw a relative performance improvement on the order of 10,000 times, but the power consumption for the system was the same.
Hi, I'm Mark Johnson. I'm a scientist at D-Wave Systems, and I work with a team of other scientists and engineers developing the superconducting integrated circuit chip that's at the core of our quantum annealing processor. We have our chips fabricated on 8-inch silicon wafers, and when we receive them back from the foundry, they look like this. Here, if you look closely, you'll be able to see a repeated array of squares that are multiple copies of our integrated circuit chips. That integrated circuit chip is really just a series of metal layers, predominantly, which you can see in cutaway here. The process that goes into fabricating this integrated circuit chip is actually not that different from that which goes into making the chip that drives your cell phone or your laptop. One of the principal differences, though, is that these metal layers are actually made up predominantly of niobium, and niobium is chosen because it's a superconductor. So the thing about a superconductor is that when you cool it down below a certain temperature, all of the electrons really collapse into the same quantum state. They cooperate with each other in the way that electrons in a normal metal don't. Now, ordinarily, quantum mechanics only exhibits on the scale of atoms, electrons, or photons. Superconductors are unique in this way in that you can see quantum behavior on a much larger scale. And it's these properties, these quantum mechanical properties, that enable us to use these materials to make our quantum processor.
All right, so I'm going to stop it there because we've already talked about what Mark's about to talk about. Let me just pop back over to the slides. I'm happy to share the slide deck after as well, and I've included the links to the lab tour there if you're interested. But yeah, I thought maybe this would be a good time to pause and open it up for Q&A on kind of the quantum annealing section and the lab tour. Marlou, what do you think about that?
That is wonderful, Alex. Great to see the labs and the very clear lecture. Johanna from Germany says this is one of the best lectures. It is so clearly explained. Thank you very much. Can you give an indication about the second part, how long it will be for me to decide how many questions to ask?
Yeah, we have until 10:15, right? I think the second part is about 20 minutes of a lecture, and then maybe 10 minutes or so for Q&A. Maybe.
Yeah. Okay, great. Then we will go ahead with questions.
Okay.
And great that you will share the slides, and the video is online too. Let me go up to the questions. So first, about the configurations of your qubits. Miguel from Mexico asks, do you only use nearest neighbor interaction, or could you also use longer range interaction in the Hamiltonian and in the chip layout?
Yeah, so I think if I'm interpreting the question correctly, it's would it be possible to connect maybe, I don't know, a qubit here with a qubit way across the chip? And the answer is that for our processor, it's not. As if you remember, I mean, Mark didn't go into a lot of detail, but the way the qubits and the couplers are laid out on the fabric, they do need to overlap in some way. Actually, maybe I should have shown. So the last part of Mark's lab tour will show how the qubits and the couplers are laid out. And you can see that the Josephson junctions or the couplers, they kind of overlap with the qubits. So that's why going from kind of a Chimera chip to this Pegasus chip, we needed to kind of shift this structure here so that we can get more vertical qubits overlapping with the horizontal ones. Short answer is we need some overlap in order to couple the qubits together. I'm not sure if Sarah wants to add anything beyond that.
Yes, let's continue with the next one. And in the meantime, Sarah,
I just have one thing to add to explanations that Alex gave. So physically, that is correct that we cannot, connect, for example, one qubit on one edge to the other. But all of these chips are able to be mapped into a fully connected graph. That means that the whole size of the processor might go from, a 5,000 to 100 if we are trying to map it into a fully connected graph. But although they are not physically connected, but we can connect, a number of qubits and call them another secondary qubit, and then all these secondary qubits can be all connected. So that is possible.
Mm-hmm. Then looking forward to the next one. Sharma asks, how can you control magnetic fluxes in such a dense lattice of qubits?
Ooh, yes, that's a good question. We have, oops. Oh no, okay, let me pull that back up. There's a slide that I didn't share, but we have, there's a lot of on-chip control circuitry is kind of the short answer. So there are a number of on-chip DACs, digital to analog converters, that hold flux and apply that flux to the qubit and to other kind of circuit elements around the qubit to compensate, to control, to control the anneal, to control the biases, and to compensate for like fabrication inconsistencies. That's my short answer. Sarah, do you have anything to add?
Wonderful. Then also feel free, Sarah, to answer, or Alex, as you prefer, you are both the experts. Abdallah from Algeria asks, does temperature play some role in reaching the ground state, the global minimum at the end of the annealing, and support the quantum adiabatic theorem?
Yeah, the temperature is really important. And so that's why we have so much kind of shielding and have put so much care into developing the refrigeration system. Any fluctuations in temperature can impact the anneal and kind of support the processor to jump into an excited state.
And similar might hold for magnetic fields. Mohammed Shuram asks, in the ultra-low magnetic environment, do you cancel the effects of the Earth's magnetic field? If so, what do you do to achieve that task?
Yes, great question. So we have a lot of shielding around the chip and the control circuitry to cancel out the Earth's magnetic field. We have some other ways within the processor as well to kind of cancel out any additional magnetic fields that might be generated by the room temperature lines and things like that. I don't know how much detail we're allowed to disclose about that, but yeah, we have many ways of removing all of the magnetic fields.
Wonderful. Juliana from Italy asks, what is the best strategy to represent a complete graph on your hardware? And she also has a more detailed part of their question, but please go ahead first.
Okay. Yeah, so we'll see in the next section that when we're embedding something like a complete graph on the chip, we have to go through a process called embedding. So that's like what Sara said, where we can group qubits together to represent a logical variable in the problem. We have specific embedding tools to get good quality embeddings for cliques, so a fully connected graph. And then we also have more general embedding tools for other kind of sparser graph layouts as well. But yeah, embedding is the key there, and we'll see that in a little bit.
Great, and look forward to hearing more soon. David, US, there is of course always this question, what are the limitations of D-Wave computers? Can D-Wave solve problems besides optimization?
Yeah, that's a good question. Quantum annealing is really kind of suited to optimization problems and some kind of quantum simulations. So there are other like gate model computers that are better suited for other types of applications that involve like differential equations or computational fluid dynamics or quantum Monte Carlo simulations. You know, there's a whole other category of problems that are better suited for gate, but annealing tends to be the best choice for optimization problems, even when compared to QAOA.
And Sara, if I'm not mistaken, you are working on gate model-based computing now at D-Wave. So D-Wave has decided to go for both strategies, perhaps depending on the application.
That is true, and as Alex said, the main reason behind that is so there are certain type of problems that suit quantum annealing better, and there are certain type of problems that suit gate model type of computation better. So that's why D-Wave decided to continue with both models, so we will be able to solve a wider range of problems that comes to us from the customers.
Very exciting. I don't know how much can be revealed about that yet, but we will see at some point how you are implementing it and how you build on the expertise with quantum annealing for your Super B gate model-based computers. There are more questions, but we can also switch to the next chapter first and then ask the rest of the questions at the very end, because we are curious to hear more.
Okay, yeah, that sounds good. Yeah. Let me just move down here.
While starting it, Amirali, who put up his hand at the pressing question, given the transverse field term causes the model to become quantum mechanical by making it non-commutative, how does this in turn slow down the dynamic of the system to get the classical result? advanced question at the end.
Sarah, that sounds like a great question for you.
Do you want me to answer it now or?
Yeah, go ahead.
Can you repeat the question for me, please?
Given the transverse field term causes the model to become quantum mechanical by making it non-commutative, how does this in turn slow down the dynamics of the system to get the classical results?
That is the, so we are turning that quantum term. So that was the time-dependent coefficient that we had in front of it. So all of those terms, they have a time-dependent parameter that controls their amplitude. So by controlling that amplitude, we can change it.
Wonderful. And I'm sure, Amirali, if Alex and Sarah have time to stay, that you will have many questions and discussions for them. Please go ahead with the next part, quantum programming and applications.
Great, thanks. And you can see my full screen presentation mode. Yeah, okay, sweet. Okay, so yeah, next I wanted to kind of connect the what we learned about quantum annealing and the chip itself to how we might use a quantum annealer to solve an industry application. So we'll talk about from an industry or an application perspective, the model that we use, and then talk about or go through an example to go through like how we would move through that problem formulation process. I'll show you a demo of our cloud software or a cloud platform. I'm just going to move this out of the way. And then I'll wrap up by talking about a few applications, though there are many more. So again, I have more links that you can explore later in the slide deck. All right, so given what we know about quantum annealing, how would we then use a quantum annealer to solve a real world problem? I know we just spent, I don't know, maybe an hour talking about quantum annealing, but to use the QPU, we've tried to design our system and our software tools in such a way that you don't need to know the physics to be able to use it to solve problems. So when we're coming at this from an application perspective, instead of thinking about the transverse field Ising Hamiltonian, instead we're just going to think about that second term within, or the second term that's multiplied by the B of S coefficient when defining our problem. And we're even going to use some different language when we talk about that equation. So we're going to call it a binary quadratic model. You may also see it referred to as a QUBO, quadratic unconstrained binary optimization problem. But either way, this is essentially a collection of linear biases on a variable and a collection of quadratic biases. So here our x's replace the qubits that we saw in the Hamiltonian, and A and B represent or replace our H and J terms. When we want to formulate a problem to solve on our quantum computer, we tend to go through a few steps. So we'll start by defining what our binary variables mean. Then we'll define an objective function. So that's the overall quantity that we want to minimize or maximize, the thing we want to optimize. And then when we're talking about real world problems, we always have rules that tell us what solutions are feasible and what aren't. So mathematically, we call those constraints, and we have to formulate those as well and add them to the model. So now I want to go through a really simple example of selecting locations to place antennas to kind of demonstrate this process. So let's pretend that we're talking to a cell phone provider and they come to us because they want to extend their coverage throughout an area. So what that entails is building additional antennas that will service a specific area. Each antenna can only cover a particular radius around it, and that's indicated in this plot where we have kind of the red dots represent existing antennas, and then this kind of donut or light red circle around it represents the area of coverage that that antenna can service. So this here is a map of Germany. The green dots here represent viable sites where we could put antennas. And the problem is we want to build new or select sites to build new antennas so that we maximize coverage. On the right here, we have blue dots that indicate what the quantum processing unit has decided good locations are, given a few other constraints. So we're going to look at a much simpler version of this problem to go through this problem formulation step. And the way I would start to think about this problem is by kind of mapping it out as a graph, where our nodes in the graph are going to represent possible site locations, and the edges in the graph represent interference between two locations. So if we were to select both 1 and 3 and build antennas there, then there would be interference. That's what this edge here means. So then the optimization problem becomes that we want to maximize coverage without introducing interference. So we want to choose as many site locations as possible. If you're familiar with graph theory, this is just a maximum independent set problem. All right, so if we start by thinking about our objective and constraints on a high level, we're going to say that the objective is to maximize the number of nodes chosen. The constraint is going to be that we can't include any edges in the set of chosen locations. So here, this is one possible solution where we've chosen location 1, 5, and 7. The orange nodes indicate the set that we've selected, and we can see that we don't have any edges in the set because there's no edge between 1 and 5 directly. There's no edge between 5 and 7, and there's no edge between 7 and 1. So this is both a feasible solution, and in this case, it turns out it's an optimal solution. There are actually 4 optimal solutions to this graph. Our next step would be to start formulating the problem, but before we do that, we have to kind of decide what our binary variables mean. In this case, our binary variables are going to mean whether or not we've selected a site. So if they're 1, we've chosen that site to build an antenna at. We're going to have a binary variable for every node here. So you can see that in this image here. And our final solution to the problem will be values assigned to these variables, and the values indicate which sites we've selected. So x1 is equal to 1, x5 is equal to 1, x7 is equal to 1. That means we've chosen these orange nodes, whereas all of the other binary variables are going to be equal to 0. Oh, and this is this set of binary variables and the values assigned to them would be what we'd receive from the QPU. Okay, our next step is to formulate our objective function. So remember that for this problem, we want to count up as many nodes as possible, or we want to choose all the nodes that we can. So to mathematically represent this, we can just add up all of the nodes or all of the variables that have been selected. This will give us a count for the number of nodes selected. And then we maximize this by just including this max expression out front. But if we remember that quantum annealers, they minimize an energy landscape, they don't maximize it. So that just means that we have to recast this maximization to a minimization. And we do this by just multiplying by -1. Once we do that, it's naturally become a minimization expression that we can pose to the quantum computer. The next step is for us to formulate our constraint. And we're going to do that by building a penalty model. So a penalty model works by kind of penalizing the configurations that we don't want, that are undesirable. And we're going to start thinking about this with a truth table. So here I and J represent two nodes in our graph, and the zeros and ones here indicate the possible states that they can be in. So here are all of the possible configurations if we just look at a two-node system. Here, if we have I and J is equal to 0, what that means is we haven't selected either node to be included in our final set. So that might be like 5 and 6 here. We don't care if they have an edge because we haven't selected them. So they have no meaning in our solution. When we look at the next two entries, so where we've selected one node but not the other, this is a configuration that we're very interested in. It might be like looking at node 1 and node 3 is one example of this. So we've selected node 1, we have not selected node 3. We don't care if there's an edge between them because we won't end up including that edge in our final set. So, okay, that's good to know. We're not interested in that particular configuration. If we look at the last entry in the truth table, we've selected both nodes, so I and J, and that's represented by what I'm showing here with node 1 and node 2. If we select both node 1 and node 2, and there's an edge between them, that means that we're including that edge in our final result. And that means that there's going to be interference between the antenna at 1 and 2. So we don't want this. We want to penalize this situation. So we're going to do that by adding a cost to that configuration. And here we're going to say that that cost is 1. The exact value you choose is arbitrary. But we're going to say that the other 3 states that we don't care about, we're not going to add a cost to that because all of those states are just fine. They don't negatively impact the solution that we get. So we can use this truth table then to solve a system of equations. This is the equation that we would build the system from. And if we solve that system of 4 equations for A, B, C, and D, what we arrive at is this expression here, where C is equal to 1. So we just have a quadratic term, and we want to sum up over all of the edges in the graph. That's effectively what this is doing. It's counting all of the edges that have been included in our final result. And the reason we want to do that is that the more edges in our final result that have been selected, the more that'll add to our energy. So it'll indicate an excited state, which will make it less likely that the processor will return it. Okay, our next step would be then to combine our objective and our constraints into a single expression. At the very end, like if we had a more complex problem, we would combine the objective and constraints and simplify to get something that looked more like this BQM up here. But this is a very simple problem. And so just by adding the objective and constraints together, we already get an expression in that form. So here our linear terms are represented by the objective and our quadratic terms are represented by the constraint. You'll notice that there's this gamma parameter here that I'm multiplying the constraint by. And we use this gamma parameter to tune the problem or weight the objective relative to the constraint. So this is important because it allows us to, well, if we tune it properly, we'll get solutions back that where all of the constraints are honored. So we'll get feasible solutions back, but the constraints won't overpower the objective. So we'll still get optimal solutions. So there's kind of a fine balance of tuning these Lagrange parameters when we have constraints along with an objective. But that's a little beyond this lecture. I just wanted to mention it though. Okay, so now I want to show you LEAP and give a little bit of a demo. I'm just going to pop over here. You can see the web browser now, right? I can't see any.
Yes.
Okay, great. So if you were to go to Google and search for, I don't know, D-Wave Leap, it would be the first link that would come up. It's free to sign up for a Leap account, and you get 1 minute of QPU time if you do. Leap isn't available in all countries or regions, unfortunately. It is available in North America, Europe, Australia, India, Japan, Singapore. I may be missing a few others, but if you go try to sign up for Leap and are unable to or reject it, it's because we don't support your region yet, but we're always expanding. Anyways, in Leap, we provide a dashboard that shows usage, monthly usage. We have a bunch of resources that teach on like what quantum annealing is, how to use our quantum annealers, and how to use our software tools. There's a community and a help center, so there's lots of support for learning. And we also provide an online IDE that we can run our code examples in. So we have, 47 code examples at the moment that range from real world problems like 3D bin packing or portfolio optimization to kind of fun problems that are good for learning how to use our systems like lineup optimization. And we also have some Jupyter notebooks that for learning how to use some of the more sophisticated knobs and parameters on the QPU, like reverse annealing. But the example that we have been looking at is the antenna selection. So for every code example, there will be some information on what the problem is. And this graph should look familiar. I'm going to scroll down. It'll tell you how to run the example. And then there will be some information about the formulation. So similar to what we went through in the slides. But I'm just going to go back up here, and I'm actually going to open up an existing workspace I have because I modified it a little bit so we can see what's happening on the processor. Right now, we're opening up the Leap IDE. This is a browser-based IDE. It's creating a virtual environment right now that has Ocean pre-installed. And Ocean is our open source Python SDK that we use for building BQMs, for doing pre-processing, post-processing, and for accessing our quantum computer. Usually, it doesn't take this long. This is strange. Let me just try this one more time. Oh no. Oh, I just ran this. Okay, there we go. Whew. Let's count on things going wrong during a live demo. Okay, so when we open a code example in the Leap IDE, we'll have a README file with information on it. There will be the Python files for running it. We can see where we're using some of our Ocean tools. So here, this D-Wave sampler is the object that you would use to actually access the QPU. And this embedding composite is kind of a helper object that helps us go from our real world problem and map those variables to qubits and couplers on the chip. So this is what I mentioned before. We have a special one for cliques, but right now I'm using just the general purpose one for arbitrary graphs. The typical flow of a program would be you create a graph. This is the graph that we looked at in the slides. We do have some tools for formulating a QUBO for certain like common graph theory problems, like the maximum independent set. So that's what we're solving. And then this here is where we actually send our QUBO or our BQM to the quantum computer. And you'll notice that there's this parameter here called numReads, and it's greater than 1. So what this is telling the system to do is to resubmit the problem to the QPU a number of times, in this case, 10 times. And the reason we want to do that is because the QPU itself is probabilistic. So there's no guarantee that we're going to get the optimal solution in a single run. Yeah, so we want to solve the problem many times to sample from that energy landscape, and then we're more likely to obtain the optimal solution when we run a number of samples. But okay, I'm just going to run this now. And it starts by formulating the problem, and then in real time, it's going to send it through the cloud to the QPU. Okay. And first, we'll see that it's printed out some information about our solution. It's also taken one of the optimal solutions, and so this is the original problem. It's taken one of the optimal solutions that the QPU has returned and plotted it in an image like this. But we also have this tool called the inspector that we can use to kind of inspect what's going on the QPU and within our problem. Usually it draws our problem a little nicer. This is just kind of a twisted version of this graph here, but believe me, it is the same graph. The yellow nodes are the nodes that we've selected. So variable 7, it's this one here. Variable 5, that's this one. Oh, we have a different solution selected, and variable 1, which is here. On the right here, this is a histogram that will show you all of the solutions that the QPU returned. We only have one bar that has multiple segments here, and this is because all of our 10 samples that we got back from the QPU were optimal. There are 4 optimal solutions to this particular problem, and the QPU found all of them. The height of this bar just indicates how many occurrences we had of that particular solution. But this brings up a really interesting and important feature of the QPU. So one thing that we see in industry is that sometimes folks in business or decision makers, they are really interested in having a number of good solutions or optimal solutions to choose from. And because the QPU is probabilistic and returns more than one, having access to multiple options can allow decision makers to make decisions and include alternative kind of factors that haven't been directly formulated into the problem. Yeah, so that's an important kind of feature of the QPU. Now here with this view, this is where I can see how the variables in my problem were mapped to individual qubits on the processor. So variable 7 was mapped to qubit 547 on the Advantage processor. And this edge tells us which, what other qubit this qubit is connected to. But I'm going to stop the demo here. I hope this kind of gives more context for what we learned about the processor and quantum annealing, and then also how we might incorporate it into exploring business problems. Okay, I know we're running a little short on time, so I'll try to make this quick. I just wanted to wrap up with a few applications, and I also wanted to note that in addition to our quantum computer, we've also built out hybrid solvers. So hybrid solvers use our quantum computer in addition to classical computing resources, and they enable businesses to solve much larger size problems than could otherwise be embedded directly onto the QPU. We have a number of different types of hybrid solvers that implement different constraints natively. But if you're ever working on business problems, the constrained quadratic model solver is by far the way to go. I'm not going to say more about that now, but it's just worth noting that we have a lot of different tools for solving real world problems in our toolbox. In the last few years, we've noticed some key verticals pop up, and especially since COVID hit, logistics and supply chain optimization has been of a huge interest to our customers and prospects. We've also seen a lot of use cases and interest in pharma and the life sciences industry, as well as finance. So things like portfolio optimization and even some market modeling. There are two use cases that I wanted to just quickly highlight, and then we'll open it up for questions. But this first use case is technically in the logistics and manufacturing space, but this was a problem explored by Volkswagen. So when they manufacture cars, car bodies they have to go through the paint line. So different cars, different makes and models are put on this assembly line to be painted, and then cars are painted a base coat of either black or white. And a certain number of cars of each model need to be painted white, and a certain number need to be painted black so that they can then be painted their final coat. Now, Volkswagen was using just kind of a greedy algorithm to solve this optimization problem. But the problem with that is that it results in a lot of waste and a lot of color switching. Switching colors results in waste because you have to flush the line every time. And so that involves time, it wastes material, it's bad for the environment. So there are a lot of reasons that you want to reduce the number of color swaps. When they used a quantum annealing processor to kind of optimize this process, they were able to achieve an 80% reduction in waste and in paint time by looking at this problem from a global perspective rather than a greedy perspective, like in terms of a greedy algorithm. Then the last application that I wanted to mention is one that came from SavantX. So this is actually in production right now. They help to optimize operations at the Port of LA. So you can imagine, especially with COVID, you've probably heard about challenges in ports and shipping containers building up. So they looked at how they could optimize the movement of gantries. Gantries are these cranes that load shipping containers onto trucks. They're very slow and time consuming to move. So by optimizing the movement of these gantries, they were able to load an additional 60% more containers onto trucks per crane per day. So that's a huge savings. And in addition, they also looked at optimizing the queue of trucks, or when they called trucks up to get loaded. Before they were using a FIFO model. So as the trucks came in, they were loaded. But by using quantum to more strategically choose which trucks are called up when, they were also able to reduce the turnaround time for trucks by 12%. So multiple processes were optimized at the Port of LA with SavantX. With that, I know we only have a few minutes left, but I will open it up for Q&A.
Wonderful, Alex. Thank you very much for this very clear lecture. And there are comments that people can already picture themselves at D-Wave working on quantum annealing.
Thank you yes,
also,
please.
Sarah.
Come join us.
Great. And thank you, Sarah, for joining too and having you both for questions. We will do a couple of questions and then there will be an announcement about the Q Bronze certificates, and we will announce Friday's speaker. Going to the questions. The first question, Abdella from Algeria asks, what is the advantage of D-Wave quantum annealing over other digital quantum combinatorial optimization algorithms? Are there existing benchmarks?
Yes, that is a very good question. There is a paper that we released a few years ago now where we benchmarked our annealer against Fujitsu. So I'm happy to share that, but what I've heard Yeah, so what I've heard from customers who've used both is, so there can be more optimal solutions from the quantum annealer, but oftentimes another like really key metric for businesses is having that diversity of solutions. So typically kind of digital combinatorial optimization algorithms will return the single best solution that they found, but both the QPU and our hybrid solvers return a number of optimal or good quality solutions, and that can be really, really key for making business decisions based off of these solutions.
Great. David from USA asks, what is the maximum size of a graph that D-Wave can solve?
Yeah, great question. So if you're using Advantage directly, then the maximum clique, I believe on Advantage 4.1 is about 180 nodes. But if you're not using a clique, so if you're using a graph that has a native structure, so same structure as the QPU, then that goes up to 5,400 nodes. Now, if you're using the hybrid solvers though, depending on the solver that you're using, that extends the problem size up to 1 million variables. So that's where kind of the power of hybrid really comes into play.
Very impressive. We have a worldwide audience, and Mark Carrington asks, when do you think countries in Africa will be able to access D-Wave tools?
Oh, I hope soon. I don't have a timeline for you, but that is a region that we have been thinking about and looking at, as well as South America, but I don't have a timeline on either, I'm sorry.
But that's very good to hear. Sharma asks, in general, for transverse Ising models, you can get a degenerate ground state. Therefore, the output of the optimization routine will be a sampled ground state and not a single classical one. Is this the reason for having to run the optimization several times on the QC?
Maybe, but I think also there's no guarantee that you'll end up in a ground state at all. So we don't have a fully noise-free system, so it's possible to end up in an excited state. And especially as you have more complex problems that you embed and solve on the QPU, that becomes more common. So it can actually be quite difficult to end up in a ground state at all, which tends to be why we sample often in the thousands range.
Then a question from Juliana in Italy. In her experience, the QO coefficients seem to be perceived by the hardware as fixed precision terms, like in FPGA implementations. This might be a question to follow up later to suggest some readings to improve the understanding of the ranges that she can span with coefficients. But maybe you can comment on the ranges.
Yeah, definitely. So we actually have software tools that will auto scale your ranges down to the ranges that the QPU can work with. So I believe the H ranges are plus to minus 1. The J ranges are -2 to +2, though there's this idea of extended J ranges as well, but that can introduce some weird behavior for certain applications. So we've tried to make it so that if you want to get that deep into using the QPU, you can turn off auto scale, but otherwise you can just submit your QBO with whatever range you happen to have and we'll auto scale. That being said, if you have a lot of constraints in your BQM, then you might want to do some scaling yourself before submitting the QBO to our QPU. But I'm happy to follow up to you if you have more questions on that.
Great, very clarifying. Then would you both have a bit of time afterwards to stay on for more detailed questions? Or yes, I see nodding. Great, then I will get to the last question for now and then some announcements. And for the ones who want to stay on, we will be on with Alex and Sara for more questions after that. David from the USA asked several times, some people do not believe that D-Wave computers are real general quantum computers. What are your opinions?
Sara, do you want to take that one?
I think that's a very, very old, commentary that people used to have for D-Wave. But since then, like especially in the past few years, we had so many scientific papers that they were showing and proving the quantum performance of our processors. So we had shown entanglement, we have done quantum Kibble-Zurich mechanism, we have shown some sort of quantum phase transition in our processors. And as Alex said, we have some benchmarking that showed that we were performing better than, similar classical annealers. So I think with our new processors and with all the improvements that we've done, we have proven that, D-Wave is a quantum processor and it is using all the quantum properties to perform. And it has performed in many cases better than classical counterparts.
And the results prove it. That is great to hear. I want to thank both of you for the wonderful lecture, the wonderful question and answers. And this was the only lecture with both a virtual lab tour and a live demo. We truly appreciate all these interactive and real parts. Looking back, this was the last hardware lecture of the program. We started with neutral atoms from atom computing, superconducting qubits, IBM, trapped ion quantum computing, Quantinium. We had photonic quantum computing with the Niels Bohr Institute and a virtual lab tour. Today, quantum annealing, marking the end of this series. Very happy that we had lab tours at Maybell Quantum today. Before that, MIT, Princeton, INQ, Quix. And then, as a big surprise, the second virtual lab tour today from you, from D-Wave. Thank you very much for your participation in this program. And we will see you again August 26th at the Career Fair. We really look forward to that. Please stay on for a while for the additional questions. And then first, I will get to some household items. The first one is Q-Bronze. Many of you have been asking about the certificates. First, a great success. More than 400 of you have successfully finished Q-Bronze. Congratulations. The lists have been generated on Friday. It needed a lot of manual corrections. More than 80 names and email addresses needed to be manually corrected. So please look in Canvas that your name and email address is correct. That will save us a lot of time next time, and that will mean you will get your certificates earlier. And now QWorld has the list, and they will send the certificates to you soon. It will be announced on Discord when it has been done, so no worries about that. Then the second announcement is a big one, because in this program we have tried to leverage the speakers every time and give you the best quality speakers from the best company and see views all the way from academia to startups and bigger established companies. On Friday, we wanted to organize a special lecture and a special Q&A for you. You have seen the teasers. You have guessed many persons. The right person hasn't been guessed yet. And I will open the Discord again and give some more hints. Ooh, getting close. So there was a big hint, no bell. This is a very big hint. There has also been a hint, cooling. We talked about dilution refrigerators today, but there have been big advances to go much, much cooler, which is essential for atomic clocks, essential for certain type of quantum computers. On Friday, we will have the person for you who was essential in making the first device with a laser and a magnetic field to cool down atoms. Are there more guesses? Not yet. He was also the one who was beating the theoretical limits. There was the theoretical expectation that with Doppler cooling, you could get to a certain minimum limit. But the experiments proved the theorists wrong. And This person showed that you can get even cooler, sub-Doppler cooling.
Marlo,
It is time to reveal.
shall we reveal?
Yes. William, Daniel, Phillips, we look forward to having all of you on Friday to have your personal Q&A with Nobel Prize laureate William Daniel Phillips. Looking forward, arranged uniquely and especially for you. Great, and Sharma guessed it correctly. Wonderful. Then it is time for many participants to leave, but we have Alex and Sarah still here for additional questions. Thank you all for staying. Raj, thank you for making the great reveal. And we will get back to the questions to finish the quantum annealing until we have the special event on Friday. Amirali from Malaysia asks, given that we are using Josephson junctions to put the states into superposition and then perform the annealing, could we essentially say quantum annealing models provide an exponential speedup compared to classical models?
Yeah, I mean, one way we kind of talk about quantum annealing is by can think about it as evaluating all possible solutions at the same time, which compared to classical algorithms is different in that classical algorithms need to sequentially move through a landscape. I don't know about exponential speedup. I think it's very problem dependent. But I don't know, Sarah, do you have anything to add? Or?
Yes, it is very problem dependent, and it is not necessarily related to the fact that this is a Josephson junction. So if you were making the quantum annealing on other types of platforms, the speed up term comes from the fact that the dynamics is governed by quantum tunneling rather than thermal excitation. So that is the term, and independent of the platform that you have, you can get the speed up. But as Alex said, the speed up that you get, if it is exponential or scales in other ways, depends on the problem size and the form of the problem.
Wonderful. Then a fundamental question or physics question by Johanna from Germany. What is the advantage of the compound Josephson junction compared to other tunable barriers, for example, nanowires?
I don't know anything about nanowires. Sarah, do you?
I think for us, the compound Josephson junction, it is easy for us to control because of the on-chip DAC systems that we have. So that is totally something D-Wave related, and with the DACs we can control it to the precision we want, and it works for us. So
then Sarah, you work on the gate model. Can you already reveal, Juliana in Italy asks, how many qubits you are featuring in the gate model you are preparing?
I'm not sure if I can reveal that number now. We are we are working on it, and we are using all the quantum annealing experience that we have, but I can't reveal the details at this point.
But of course, you will. We will be the first that you will inform, and then we will tell everyone right away.
So that is true. It will come soon, but not yet.
I will skip through some more questions. Abdella wants to work on it more and asks, are there certificates on D-Wave quantum annealers? Or maybe it is meant more broadly. The question is, are there certificates on D-Wave quantum annealers?
Yeah, we have an informal certificate that we offer if you've completed our training course. So we do provide training that's more focused on how to use the quantum computer and the hybrid solvers for industry problems. So yeah, if you're interested in that, feel free to reach out to me directly. I can connect you with information on that. Yeah.
That's fantastic. And you already showed great resources as well to practice and to develop skills and knowledge. Juliana from Italy asks, okay, we have addressed that. There are mixed messages now about Friday's announcement and the current lecture, but many questions have been addressed, and also many questions have been addressed during the lecture that were asked at the start. So I will watch for a final question, and otherwise we will conclude the session after many questions already, after a great lecture. You need to be quick. Yes, Yusuf from Germany, you are right. His question was, do you benefit from parity fault tolerance when forming logical qubits?
Sorry, can you repeat the question?
Yes. Yusuf asks, do you benefit from parity fault tolerance when forming logical qubits?
Sarah, I'm not really sure. Don't know what that is. Sarah, do you?
I think Yusuf is in that field, and if you can elaborate by email, Yusuf, feel free to quantum@Womanium. Then Suhair from Bangladesh for Alex. Should we contact you directly for the certification training on Ocean SDK?
Yeah, feel free to reach out. Yeah, I'm actually an instructor in the training courses, among others. So yeah, I'm happy to connect you with that material, with that option.
It's wonderful. And then more about the work that you are both doing. Sara, can you tell about your experiences? You are directly developing new processors, right?
That is true. I have been at D-Wave for a few years now, and I was first in the quantum annealing team. And what I did as part of that was, investigating the coherence in our system, noise measurements, and calibrating the chips that go into the fridges. And Alex and others help customers to connect to. So we do lots of measurements to make sure that all these chips are calibrated and perform the best they can. And then in the past while, I have joined the gate model team, where we are working on developing the gate model version of the D-Wave quantum processors. So there are lots of measurements that I do on my daily basis. It is lots of physics involved. And for all the physics or computer science students out there who are close to graduation and looking for jobs, we will be having more job postings for D-Wave, both for physicists and for in the application team. So if you're interested, please apply, and we are always happy to see new faces with new ideas.
That is very good to hear. And can you tell about your journey, Alex, which has been with a great variety of different topics?
Yeah, absolutely. My background is in electrical engineering. So when I joined D-Wave, I joined on the service and support team, mostly on the software support side. So supporting customers who are using or who are, developing quantum applications or performing research on the system. So supporting their usage, but then also did a little bit of work on the IO system in the lab, installing processors, training for supporting our field systems. But then I transitioned into a technical sales engineer position. So now I talk a lot to customers who are quantum curious, but they don't really know how to use our technology or like where they might see business value. So a lot of the conversations I have now are around what those applications are and doing research on those applications, because that's still an open research question as well.
Yes, that is fantastic to hear, and good to have examples of so many different roles. As the last question, Amurali, I know you have many questions about this topic and also expertise in it. I want to give you the chance to unmute yourself and ask your final question before we wrap up the session.
Greetings. Thank you so much, Ms. Morda. So greetings, I'm Amir Nejad. You may have heard of me. I work with ZebraKit and with Mr. Alex Khan. So I think you've talked with him before. So the quick question I have is that in the Hamiltonian models, right? The Ising model, we add the transverse field to cause the model to become non-commutative. So the order matters, hence it becomes quantum mechanical. How does that relate to getting the classical outputs? How does that? I got the physical analogy that by using that Ising, the transfer term, you increase or decrease the dynamic of the well. But mathematically wise, how does the non-commutativity help you in getting the result? Essentially, how does the importance of order assist you in getting your result?
I think math, if you want to write down the math of it and figure out how important it is, the order of that compared to the Ising model, it sort of goes down to defining how would that term define your freeze out time or the time that your dynamics freezes, and that will be defined by the order of these fluctuations that you get for that transverse field compared to the Ising terms that you have in your Hamiltonian. So I don't know if that answers your question, or if you're interested in more. Yes, as you said, it is a term that you need that extra term in order to be able to have tunneling or the quantumness in your system. So you need that. And, right.
Yes.
Yeah, the order is with respect to each other.
The reason I'm really interested in non-commutativity is that part of a great chunk of my research relies on the sequence of applying these days, like non-commutativity of quantum, to create context, right? So I'm trying to understand, because in D-Wave, we don't really have context, but it's just one run. Like we have one model, we just want to see which variable is to be chosen for the optimal result.
We will exchange some email addresses. I see some very good conversations and exchanges coming up. Thank you very much for the question, Amirali. Thank you very much for the initial answer, Sarah. I'm sure you will get in touch more. And then thank you for the wonderful lecture, including demo, including virtual lab tour, and 2 Q&As. We will see you at the career fair, August 26th. Looking forward to that. And in the meantime, for everyone, thank you very much for being here today. We will have tomorrow Q Silver, Gibran Rashid, the full session. So we will dive deep into the last part of Q Silver. Same on Thursday, the very last part of Q Silver with Shor's algorithm. And in addition, on Thursday, we will have NIST, Dustin Moody about post-quantum cryptography. How can we protect ourselves when the quantum computers will be great in 2035 or maybe even before? And then on Friday, the closing session of this part of the program, and you all know what is going to happen. Raj, I see you unmute. I will put you in the speaker too to say final words for today.
Thank you, everyone, all the participants for attending. And thank you to everybody who played along with the teasers on the memes on Discord. It was fun to play along with. And I'm glad that now you know the answer. And I'm really glad and grateful that Dr. Marlu was able to bring William Phillips to give the concluding remarks. And even though it is a ending session, he is one of the people who started the ultra cold cryogenic research and experiment with his laser cooling techniques. So it is great to have a person who come and conclude who actually started a completely new field. And for today's session, I'm extremely grateful to both Sara and Alex for being here. Excellent lecture, excellent session. Thank you for that. Also for the lab tour. And we hope that you will come back, especially on Friday, and perhaps listen to William Phillips. So you're always welcome to come back, and we would love to stay in touch with you as we at Womanium strive to advance science and technology for all people everywhere in the world. So once again, thank you, everyone. Alex, Sara, Marlu, and all of you here. Thank you.
Thank you all, and see you tomorrow.